Hey guys, this is me Nolan and you are watching Quantum Astronomy.
May 12, 2022 is a very special day because in this day this image was published. And if you don't know what this is, then let me tell you, this is the supermassive black hole in the center of our own Milky Way galaxy, which is also known as Sagittarius A star.
So this thing is a black hole?
Well, the black hole don't have any light. What we are looking at is the hot plasma around the black hole. And the image is captured by,
I know, it's NASA.
there are other space agencies except NASA, right? Anyway, the image is captured by Event Horizon Telescope collaboration. How we capture it will be there after the intro.
In order to capture the image of the black hole in the center of our galaxy, we first have to know where the black hole is. Now, as it is the black hole in the center of our galaxy, so let's zoom in to the center of our galaxy using European Southern Observatory Telescope, which is also an infrared telescope which let us see through all the dusts and clouds between us and the core of the galaxy. For last 30 years we are observing this area. Can you see these stars are orbiting something which can't even be seen? These heavy stars, which are as heavy as our sun, is orbiting something in such high velocity, then that thing must be super heavy, right? And by using forbidden magic of witchcraft and wizardry, by which of course I mean math, we calculate the mass of that unseen object, and that is 4 million solar mass.
Okay, now we know where the black hole is. But still there is one problem.
That is, though the black hole is super big, it's also super far away. As a result, it appears very small in the sky. How small, you ask? Let's divide the whole sky into 360 degrees. The Andromeda galaxy is 3 degrees. Now divide 1 degree into 60 arc minutes. An arc minute into 60 arc second. Divide an arc second into 100. Divide it 100 more and another 100 more. And this is the size of the black holes in the sky. Now, there are no optical telescopes which can capture this image. So, astronomers use their another powerful toy called radio telescope.
In this video, I'm going to tell you how our radio telescope works. How we capture the image, that will be in the next video. So make sure you press the subscribe button and the bell icon. Back to the video.
When a source emits radio signal, it goes out radially. But Earth is so far away that by the time they reach Earth, it became almost flat and parallel. A radio telescope works by scanning the sky from side to side. When it is directly pointing to the radio source, it creates a bright spot. As all the radio waves travel the same distance and bounces off the dish at the same time. When the source moves out, some waves travel more than the other, and so they meet out of phase, and so the intensity of the signal becomes zero. This time it creates a black spot. Now, how much sharp the image will be depends on the wavelength of the signal and the diameter of the telescope dish. And this parameter is known as angular resolution. Now, when we scan it with our radio telescope, we want to see the bright spot when it passes over the right side, and then a black spot in the center, and then the bright spot again when it passes over the left side. But the problem is these black holes are very far away, and so the angular resolution is too large for any radio telescope. So when it scans the black hole, it gets light from left side while getting light from right side. And this is how the image looks. It really can't tell if it has a ring-like structure or not. Now, according to the formula, in order to get a sharp image or to reduce the angular resolution, we have to either reduce the length of the receiving light or increase the size of the receiving dish. Now reducing the wavelength is not possible as smaller wavelengths are blocked by all the dust particles between us and the object. That's the whole reason why we shift to radio waves in the first place. So we have to increase the diameter of the telescope. After doing the math, we came to know that in order to capture the image, our telescope needs a diameter of 12,742 kilometers.
Well, we are not making a telescope as big as the Earth, but virtually we are making a telescope like that. And that's where computer science came in. And as this video is way too big, so it's going to part 2, where I will show you how we actually captured the image. So make sure the subscribe button is pressed.
あらあら、さようなら。